Good afternoon, everyone. Welcome back to VEX Labs, Virtual Eliezer Experiments, home of the mad scientists. Today, we are going to be learning about magnets and magnetic fields. Magnets come in all shapes and sizes. They can be bar magnets, they can be horseshoe magnets, they can even be disc magnets. Pause the video now and write down everything you know about magnets. What do they do? What do you have written down? Well, magnets have two ends. They're called poles. One is a north pole, one is a south pole. The only difference from one magnet shape to another is where the north and the south are located. A horseshoe magnet is just a bar magnet bent in a big U so that the north and south poles are next to each other. What do magnets stick to?
They stick to fridges and sometimes paper clips.
What about this? Do they stick to this? Give it a try. No, huh? All right, well, it turns out that magnets only stick to iron and steel. Good on you if you wrote that down. They don't stick to all metals. They don't stick to aluminum, and we never ever put magnets anywhere near computers because magnets ruin computers, credit cards, and key cards. A lot of you probably also wrote that down. A lot of you also wrote that magnets aren't the only things with two poles. The Earth itself has north and south poles. The Earth has a magnetic field. Interesting. Well, if you notice that the Earth has a core of molten iron, you'll start to see some patterns emerge. So what's the deal? How do magnets work? Why do they work? Why some metals and not others? And what is it that magnets are made of? The answer to all of these lies in history, and it leads us toward the idea of the magnetic field. Let's start with the easy one. What are permanent magnets made of? Permanent magnets are one of the ferrous oxides, a mineral that is called lodestone. People have discovered for thousands of years that lodestone rocks, also known as magnetite, have this marvelous property that bits of iron stick to them. You may have heard of this already if you've read Charles Dickens' Tale of Two Cities, and you read the chapter Drawn to the Lodestone Rock at the end of Book 2, where our noble and saintly hero Charles, who is French by birth, goes back into France at the height of the French Revolution to be noble and be a hero. Of course, he's thrown in jail and gets sent straight to the guillotine, and he knows this, and he knows what sort of an effect it's going to have on his wife and child, which is why the chapter is called Drawn to the Lodestone Rock, because he feels magnetically drawn by this irresistible force to do this amazingly noble and incredibly stupid thing. Let's be fair, Dickens didn't invent it. Drawn to the Lodestone Rock is actually found in the Arabian Nights, and it's a description of this rock on which ships inevitably founder, shipwrecking the poor Arabian sailors as if they were drawn to the rock by magnetism. Everybody knows that classical elves, fae, the fairies, as they're known in Celtic literature, not the nice ones that live under toadstools, the real ones from our old British roots, are mortally afraid of iron, and that the best weapon for invading fairyland and getting your child back that the fairy queen has stolen, or your lover back that the fairy queen likes and wants to keep and was one of her own harem, is a sword of thunderbolt iron. Thunderbolt iron is another name for lodestone, which is why Magrat in Terry Pratchett's Lords and Ladies finds out that she is actually able to be less than useless when she finds an old suit of iron in the armory and discovers just how much the fairies don't like it. Tiffany Aching, 9 years old, will do one better on her for the wee free men and invade fairyland using her trusty frying pan with marvelous results. Now, Sir Terry Pratchett worked for Britain's Nuclear Electricity Board before he became a best-selling world author, and he has the fairies describe why it is they hate iron so much. They describe these magical lines of force that they use to see, and they say that the iron messes up the patterns somehow. These are iron filings, powdered iron. If you happen to have a shaker of them in the pantry, like Mr. Reimer does in the chemistry lab, you can do this at home. I'm spreading them nice and thin so we can see. And we know that iron is the metal that is the most sensitive to magnetism. I'm going to take this permanent magnet, which I've wrapped in plastic wrap, and I'm going to pass it under the iron. Our complaint for electric fields is that we didn't have any test charges to see them. That problem is now solved. Can you see the lines of force? Can you see the magnetic field lines from this permanent magnet? Sorry. Does this diagram look familiar somehow? Maybe like something you have in your notes from electric fields? Pause and look it up. Press play when you're ready. Let's try this from above. Field lines go up. Field lines go... Well, the problem is we don't have any arrows. We can see the direction of the force. We can see the actual field lines hanging in the air, but we can't see any arrows yet. Draw the field lines in your notes. Draw the field lines from north to south around a bar magnet and around a spherical magnet. Done. Here we are, ladies and gentlemen, magnetic field lines. Magnetic field lines around a bar magnet, magnetic fields around a spherical magnet. That's what the Earth is, everybody. It is a spherical magnet. North Pole, South Pole. Truth in reporting, magnetic north is a couple degrees away from geographic north, but that's why they call it the North and South Poles. Want to see it in 3D? Here you go. Check it out. See the field lines forming around the permanent magnet. Look at the filings and you can see the curves. Now show us your toy there, Shani. How does it work?
You have to do this, and to erase it, you flip this little switch on the back.
Anybody who has an Etch-a-Sketch or Magna-Draw, this toy has iron filings suspended in oil under the plastic. If you get a magnet anywhere near them, the iron filings will stick straight up in the magnetic field. They'll poke through the plastic screen and you can see them. To erase, there's a magnet on the back. You're not erasing them, you're pulling them away from the front of the screen toward the back. Show us.
So I figured something where you do that and it looks like they're all rolling their eyes.
3 applications I want to make clear. First of all, we are staying away from the word charge. Nobody on their list said that a magnet is a battery or can function as a battery. Magnets are not batteries. They do not have positive or negative charges. They have magnetic poles. What else has a magnetic pole? A compass. A compass is a magnetite needle suspended in oil so that it's free to turn. When left to turn, it points in the direction of the Earth's magnetic field. We had to figure out what magnetite was like in order to use these lines of force to navigate by, but birds do it biologically. You all know that birds migrate. They go from north to south when it's winter in the northern hemisphere, and from south to north when it's winter in the southern hemisphere. Pause for a second and hypothesize as to how birds know how to do this. Let's get one thing straight. A common hypothesis to start off is that birds have magnets in their beaks, and those magnets have a south pole that's magnetically attracted to the north pole, which means the birds are dragged, flapping their wings, going north across the sky like this, even though they're facing forward. All right, when we're done laughing, let's scrap that hypothesis. Birds do not have magnetic beaks, bonk, and they're not attracted to the North Pole. We need something a little more subtle that will allow the birds to move. Check it out. Here's a magnet, and this other magnet in my hand is providing a magnetic field. Notice that this magnet can move in the magnetic field, but it can also turn. Check it out. Turning until it's aligned with the magnetic field. Turning until it's aligned with the magnetic field. Birds have 2 tiny lodestone crystals in their beaks, and those crystals turn to align themselves with the Earth's magnetic field. They serve as an internal compass for the birdies so that they can tell which way is north and which way is south. Pause and think of a good way that you could test this model actually true. Ready? A group of birds was raised from the egg in nests in a laboratory with plenty of fresh birdseed and water and a giant magnet running east to west across the laboratory. The birds were let outside on the roof for regular exercise and lovely rooftop gardens with cages on top. And when the weather turned cooler, the cages were removed and the birds were let free to fly, to migrate wherever their instincts took them. Sure enough, this group of birds in the magnetic field migrated straight west as fast as they could go. And you know what? You know what they found after a couple dozen miles, after a few hundred miles when they were on their journey? They found another laboratory, just like the one they'd been raised in, with a rooftop garden and plenty of fresh birdseed and water, and the nice people in white lab coats all ready to welcome them to their winter home. And the birds thought, great, just like home, and they settled down west of the lab for the winter. And in the east, and in the spring, they migrated straight east again, because they had been raised in a very strong, artificially generated magnetic field. Their internal compasses had calibrated east-west instead of north-south, the way the magnetic field of the Earth goes. And that's how we know how non-human animals migrate. They migrate according to the magnetic field lines. Notice that the red part of a compass needle, the North Pole, is the part that points south. North is attracted to south, and south to north. Opposites attract, just like in electric charge. This is where the misconception about electric charge comes in. You can make your own compass at home with a steel needle suspended in water and something you can float, and by bringing a magnet close in, you can temporarily magnetize the steel and draw your own little compass around. Try it at home. In our next lesson, we'll discover what Hans Christian Ørsted discovered quite by accident and explain why this particular mineral has the properties that it does, why iron and not aluminum or any other metal, where these lines of magnetism come from, and most importantly, which way the arrows go. I will see you then.